Thank you. So, it's indeed my pleasure, privilege, and honor to be doing this colloquium here today, which is really in honor of the both the laureates of this year's physics prize, as well as a substantial community that has been involved in attosecond physics, which, depending on our perspective, may have started 30 years ago, or as I may want to say, maybe even 100 years ago. I hope to convince you through this talk that this is a very exciting area of science, and that there is plenty of not just room at the bottom, as Feynman said. Hopefully by the end of this talk you'll be convinced that there is also plenty of time at the bottom. So, notional outline of this presentation. So I will introduce the prize and the prize winners themselves, and considering this is a broad audience of physicists, scientists and engineers, also would like to motivate what is an attosecond and why this adjective. A good part of this field is physics, techniques, technology and so on, all done by physicists and engineers who have basically, let go of their identities and come together to create some very exciting avenues of science. So what made it possible in the 2000s, the roads to this milestone, what paved this road? I'm probably not going to be able to do exhaustively. There would be some amount of subjective opinion on who are the major contributors and so on, which sometimes could be controversial. Hope I don't quote any. The Nobel Prize can only be given for 3 people, and which simply means that there are many others who possibly made very important contributions who've been excluded, right? So there are very important players in my opinion, but then I will also try and bring about their critical roles, because as Newton said, we stand on the shoulders of giants to create new science. And then what have we done as we, meaning as the human race, with on these timescales and this science and technology, and what can we do with it? Possibly also motivate some thoughts so that you're convinced that the physics and the technology that it brings, which has a give and take relationship, lead us to a bright future. So what is this prize about? This prize was given to 3 people, Professors Pia Agostini, Ferenc Krauss and Anne Lullier. Maybe I should have said Anne Lullier, Pia Agostini and Ferenc Krauss in terms of the chronology of their contributions. The prize was given for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. A fairly straightforward statement, one would say. So this is probably the best summary of this talk, or abstract for this talk in itself, and we will try and figure out both the generation, I would call it make and measure, of attosecond pulses, as well as electron dynamics in matter. So what is an attosecond? So if you want to feel it, our heart beats at about 1 hertz. The age of the universe is 10 to the 18 hertz. So if that gives us a feel, our 1 second contains as many attoseconds as the present age of the universe contains seconds, but it's going to take a long time before the age of the universe is going to escape that ratio, right? So that's for a common field, public science. But then for a physicist, engineer, scientist, or any curious mind with a little bit of mathematical knowledge, which I would say includes only up to calculus, we can do a kind of computation. Everybody knows about the radius of the Bohr orbit from high school physics. So take the circumference of the Bohr orbit, then take what we physicists will call the expectation value of the electron, which is the measurable value of the electron, if you can measure it right there, maybe with a fictitious point detector without disturbing the atom, if one exists at all. It turns out to be a something of physics quiz trivia. It is c, the fine structure constant, times the in vacuo speed of light, which turns out to be, this is about a factor of 100, so 2 times 10 to the 6 meters per second, right? So now we can, if indeed, as originally thought of, the atom had, electronic structure of the atom was very classical, very planetary, then this planet would have gotten around, the electron as a planet would have gotten around the nucleus once every 150 attoseconds. That's the circumscription time. But then this is the electron's orbit period, and before my physics experts in this audience scream out saying this is the wrong picture, yes, it is not the right picture. So I'm going to use Professor Einstein, who always asks us to think from time to time. So think, if such a number comes out of a simple back of the envelope calculation, and then it is not the right picture of the physics, then how do I rationalize this? Okay, so we go and pull out our quantum mechanics textbooks, because we know that atoms are essentially quantum objects. All objects are quantum objects, but these are very, very quantum objects. So let's write down the Schrödinger equation. You can also write down the Dirac equation, doesn't matter. Both will lead us to very similar results. And then in this lecture, we are not going to solve the Schrödinger equation. We're going to use the style of one more great mind who said, I consider that I understand a problem when I can predict things about it without actually solving it, which was none other than the remarkable Dirac, who's actually looking at the hydrogen molecule in this chalkboard, right? So all we want to do is to construct, as we should in any physics problem, a good physicist should try and construct the natural scales of length, mass, time, energy, even magnetic flux, whatever you like to do, right? So here in this equation, we have at our disposal the Planck's constant, the mass of the electron, the mass of the proton is there, but let's not take that up for the moment. It's a subject for another discussion, and the unit of electronic charge which the electron carries. So if I try and want to build the a unit of time based on this, which we will formally call the atomic unit of time, the quickest way to note that is to write down the fine structure constant, which is a very important number, and it's also dimensionless. So essentially the fine structure constant is dimensionless, but then it has c, the speed of velocity in it. Legally, I'm not allowed to use c because that doesn't appear in the equation. Nonetheless, taking advantage of this, e square divided by the Planck's constant, with c in the denominator would have given me the fine structure constant. Because of SI units, we have a 4 pi epsilon naught. I will also keep it there because people like to use it, we like to use it, experimentalists live on that. So this has the scale of a velocity, and then we have the scale of energy coming from it. Take the mass and multiply the square of velocity from it, and then we know that time is Planck's constant divided by energy, right? So this turns out to be a unit of time, which is essentially 24 attoseconds. Okay, so whatever we do in the atomic world, when it pertains to electrons, this would have been a very good unit of time to measure everything else in, right? So this is the natural time scale of the electron. There has always been a talk about ultra-fast physics or ultra-fast science. So how fast? 30 years ago, ultra-fast was pico and femtoseconds. Today, it is attoseconds. Maybe 10 years from now, people are going to call zeptosecond the ultra-fast time scale. Okay, so maybe in the early 40s, it was milliseconds. In the early 1900s, it was even slower or whatever, right? So what sets the term ultra-fast into motion is basically the natural time scale of the object that we are trying to study. If it was a horse galloping, maybe a second, or more appropriately a millisecond, would have been the right scale. For electrons, this is the right time scale. So we have hit the natural time scale for electrons, not just on the back of an envelope like this, but also on the experimental table. That really is the remarkable achievement which the 3 laureates of this year and their collaborators, colleagues enabled. So an attosecond is something about the atomic unit of time, natural units. In that sense, I hope I will also convince you that this is also the time at which, period at which if the electron had a heartbeat notionally in maybe science fiction or in comics, this would be the right time scale to use. And it is not so much like the electron is going around the nucleus, right? So let's extend this, the quantum mechanical picture further and go a couple of chapters later in our textbook and create what we call an electron wave packet. So an eigenstate or ground state of the system is essentially written using these symbols, psi, which is a function of r and t, space and time. So we have the spatial part, which will give us the stationary state and the orbital, and the temporal part is here in the complex exponent. So now what we can actually measure in quantum mechanics is related to the mod psi square, so it's the electronic probability densities in this case. This now starts to sound like a quantum mechanics class, and that's purely intended. And if I look at the 1s, 2s and 2p, the first three states of the hydrogen atom, then essentially the radial probability density function looks like this, and we can make nice colorful pictures of it. We will soon do that. Now, if I now take two states and then somehow form a superposition of these, that's what I would call an electronic wave packet. Okay, so there are two waves and they are coming together and forming a superposition. But what I can once again measure of this family of two is the mod psi square of this wave function. So just like in a conventional double slit experiment, we have two static, relatively boring terms, and here we have a dynamic term which is like the interference term. So that already tells us that some dynamics kicks in, right? So we can ask the question, what is the natural time scale of this dynamics? So this dynamics essentially has a time constant which is essentially h divided by the difference between the eigenvalues of energies of these two levels. So it's h bar divided by the delta of this E. So now the larger the E, the faster the dynamics. Okay. So this is one other reason or way why we should consider attosecond time scales. Well, I've already made my first typo in this presentation. This should have been 2p because this wave function pertains to 2p. But then let's write down the radial wave functions for the 1s orbital, which is 1s here, with reference to the continuum, which is when the electron gets free. If I set the 0 of my energy scale there, then the 1s level is 13.6 electron volts below it, whereas the 2p state is about minus 3.6 eV. So we only care about the difference. I'm also doing a back of the envelope, so it is an approximate value. So if I now plug in delta E over here and write down Planck's constant in this slightly unusual but very useful unit of electron volt multiplying femtosecond, pop comes the answer that these two states, when superposed, God knows what dynamics they will do, but that dynamics essentially happens on the time scale of about a few hundred attoseconds, right? So a cartoon visualization, but fairly accurate, of the atomic orbitals during this dynamics kind of looks like this. I'm plotting the mod psi square, the electron densities, and they are jiggling around like this. And so this, if anything, would be the right picture for an electrons movie. So we can create wave packets. So we have accidentally or otherwise created attosecond wave packets right now in this hall and on my computer screen, right? Wish life were that easy, because the laser was invented in the 1950s, and here we are in 2020s, just reaching about an attosecond when we are able to do things in a laboratory. So attosecond electronic wave packets operate on attosecond time scales. What about pico and femto? Now, if I take a molecule, make a molecule out of 2H atoms and then look at the natural dynamics of these two nuclei or atoms, they're going to breathe around, so they have vibrational motion. Vibrational dynamics takes place on time scales of femtosecond. You measure it in femtosecond, so you will see results in the picosecond domain also. Now, what about picosecond dynamics? So, if I take a more significant molecule with 3 atoms, then like water, a triatomic molecule, preferably bent maybe, this is a good illustration, then this molecule rotates. And this time scale is on picoseconds. In as much as we should not think about an electron revolving around the atom's nucleus in a planetary motion, we also should not think about these motions in the form of, in whatever classical minds actually tell us, although we use it very often even in the classroom. It's not really a spring that is just stretching out, because this is a classical oscillator. We should really think about the quantum simple harmonic oscillator. But more interestingly, also for vibrational motion, in order to actually create a molecule's rotational motion, we actually need to superpose a couple of vibrational eigenstates and create a wave packet. So in the atomic world, everything is wave packets, wave packets, wave packets. Otherwise, life gets pretty boring. And so in this lecture, we're going to talk a lot about wave packets. Okay. So now, an analogy. I kind of maybe slightly provocatively said there is plenty of time at the bottom. We all already know there is plenty of room. So I did not feel it necessary to include that. But then we are all hungry for quantum or quantumness, especially in today's age and time, because we have quantum computers on the way and so on. But even otherwise, the entire universe breathes on the Planck's constant maybe. So, but visual effects or visible effects of the quantumness of the universe, we know comes about by simply peering down microscopes. We take the size down, go down and look on atomic scale, and then we see beautiful quantum statics, dynamics, or patterns. This quantum coral is an iconic image coming out from IBM. Likewise, if we do the same in the temporal domain, go down to the natural time scales of all these quantum objects or any of these quantum objects, we are going to, of course, see a lot of manifestation of very exciting quantumness or quantum behavior. So much so that, as Walter Levin likes to say, once we see it, we can't unsee it. So that's essentially the merit and goal of attosecond science. Of course, science is also done by human beings, and so we all like to be successful and much more than that. So this science has in a way made a sort of silent revolution all the way from late 80s and 90s, when the pioneers in this field toiled out and brought about some nice techniques and technology, to where we stand today. This is a burgeoning field of research. This is not to say that other avenues in research are not exciting. They are pretty much as exciting, but maybe this field was looking for some recognition when really important problems on much larger time scales or much smaller time length scales are indeed also our concern as physicists. Yes, Sriram. Yeah, great question, Sriram. So these are, this is a scanning tunneling microscope image. So this is indeed is a measure of the electron density. Basically, it is something proportional to the local electron density. So basically, an STM tip, and I'm sure there are better experts on STM technology over here. It basically scans this whatever surface we give it and measures a quantity that is proportional to the electron density. But then, in today's world, if you want to carry news fast and viral, apparently, you got to put a no in the caption. So it's indeed true that there are strictly no attosecond lasers on the table. That's also why I don't think in the press release or any document you see that. But in a lot of popular media, you see attosecond lasers, right? So by a laser, I mean something, you take the box, plug it into a wall plug, and here we should say, if there is power, then you should get the desired beam out. So we would say, okay, take the box, plug it in, and then you get attosecond pulses out. We are not yet there. That is to say, there are no purely electrically actuated attosecond sources. We'll have to make these out of something else, and I'm being a little bit picky but careful in excluding accelerator-based sources, which are touching the attosecond limit and as we speak getting there. I'm not going to talk about them at all in the source because the price itself concerns attosecond pulses which are made on the table, but I'm pretty sure that in the coming years important things will happen due to accelerator-based photon sources, which I also personally like very much. But then how do we generate these light pulses? If we look at this chronology, one of the things that we always talk about is electronics versus photonics, though it's probably not the right way to think about things. Electronics, the switching cycles in electronics have come down pretty fast. So all our computing devices operate at several gigahertz, let's say about max 10 gigahertz, especially in hands-on electronics. Photonics has always been faster in the sense that the briefest processes that we can measure and play with in photonics has come down to about a few femtoseconds in the year 2000. But then here there is a knee, there is a cusp. Something changed in terms of techniques and technology which made this possible. What is that? So that essentially is the reason why somebody got the Nobel Prize this year. Okay, anything good that happens with photonics is always lasers, lasers, and more lasers, right? Despite my personal biases, this is indeed true. So the citation honoring Professor Anne Lullier, she is a professor of atomic physics at Lund University in Sweden, says Anne Lullier discovered that many different overtones of light arose when she transmitted infrared light through a noble gas, and she has continued to push this field. Indeed so, and I can also vouch for that personally. I took a couple of workshops where Professor Lullier was the teacher and lecturer, and she's a great teacher too. So this is essentially the process. You take some gas in an appropriate vacuum chamber, send in near infrared light. So near infrared, in this case, 800 nanometer light, but she used invisible infrared light at 1064 or 1035 nanometers, slightly different laser, and then focus it through and you get attosecond pulses out. It seems as simple and straightforward. It certainly is not. This was done in 1987. But then what did Professor Lullier see? And in this paper which they sent to a rather robust traditional but not very flashy journal, which now has about 2000 citations, they say that multiple harmonic conversion of infrared radiation in rare gases was observed. So if you look into her interviews, she actually says that she was studying fluorescence from rare gas atoms and simply wanted to study this as a function of the light intensity of the pump laser. And this was of course done in France. So what did they actually observe and how did these attosecond pulses come about? I want to take two quick steps back and remind ourselves as to what a laser is. A typical laser is a resonator with two mirrors plus a gain medium. This is what all of us physics teachers tell you, right? So essentially there are oscillations inside, cavity modes, and one of the mirrors has a reflectivity significantly less than the other, which is as close to 100 as possible, and it couples the light out like it's happening in this laser, and light comes about, right? But we are talking about pulses over here. So what is a typical pulse laser or a generic pulse laser? In a generic pulse laser, just as we have to insert the objective, we need to insert something else into this medium. We put a pulse shortening device. And my favorite question to a class is, why do you put the pulse shortening device inside and not outside? Okay, but basically simple, in a way common sense dictates that if I put the device outside and try to make pulses, I'll be throwing away a lot of energy, which is already hard to convert from wall plug to photons because lasers are inherently not very efficient devices. 30% already is big news. So put the pulse shortening device inside, do something and produce pulses out. That is a generic pulse laser. Now, what happens inside a laser cavity? These pulses basically bounce around between the two mirrors, and every time they impinge the output coupling mirror, a pulse comes out. Therefore, all pulse lasers typically produce periodic output pulses. And if we do this very well and nicely and take care of the modes and their synchronicity, which is in some sense the overtones of the cavities natural frequencies, then essentially we do what is called mode locking. We lock the modes in temporal position, and what we produce is an interference pattern in time. Okay, so in typical interference patterns, the horizontal axis is x. I've not even bothered to name one here. Here the horizontal axis is t, and all these light waves come together and synthesize to form a pulse. So this pulse, if it was optical, is already femtosecond, because optical at visible frequencies, let's say between 400 to 700 nanometers, the oscillation period of the electromagnetic wave is already a few femtoseconds. So these are all pretty nice, exquisite femtosecond pulses, and a laser that can produce such few cycles per pulse would be not just somewhat challenging to run, but also pretty expensive. So these are very high quality pulses. So now, after having made very high quality femtosecond pulses, we are sort of ready to make attosecond pulses. Yes, Srinu.
A couple of slides back, you had a pulse shortening
device. Yes.
Now, I mean, what is its role? I mean,
yes.
What would be its role? I mean, if you have a device which can shorten to any extent, then.
So I'm glad Sriram is asking questions because they're always very good questions. The point is, if I had a device that is somehow able to switch things to make very short pulses, and I am claiming to make the shortest pulses in the world, so then where did this device come from? That's the actually pulsing device. The rest is just some pump of energy, right? So that's the very interesting thing, and I didn't want to go into the details. The only thing that the pulse shortening device here should do is modulate the gain or loss in the cavity at the eigenfrequency of the cavity. That is 1 over the round trip time. That's the job of the pulse shortening device. So it could be a modulator which modulates somehow the loss in the cavity. So early on, people actually put this mirror on a fast rotating spindle, and whenever the mirror misaligns, it introduces loss in the cavity. So they tried to basically introduce selective loss and gain by spinning the mirror around. But that of course makes the mechanical stability of the laser go for a toss. So then you started using acoustic devices or electro-optic devices to do that. But finally, the most successful way of building a very stable device is to do everything so-called passive. Passive devices are very good. So we have saturable absorbers which do that, and today actually a Kerr medium is just inserted in of the right size and the laser mode locks and it gives us these pulses. As of today, there is no fundamental limit. You can literally propagate one full cycle because the laws of physics require that we need at least one full cycle for the wave to propagate. So indeed, such so-called single cycle pulses have also been produced in labs, and in fact, they even have a role in. Yeah, so the typical gain medium that is used here, the most popular 10 years ago was titanium sapphire, so aluminum oxide into which titanium ions are doped. It is essentially a gemstone. The first laser was made out of ruby. Now it has gone to sapphire, but red sapphire, not blue sapphire. But then natural sapphire is not very good in terms of control doping and thermal properties. So this is lab grown. We need tiny crystals of that. Now currently ytterbium based systems are becoming much more popular. For the pulse shortening device, you essentially want this pulse shortening device. There is one condition though, that if it's a passive device, its natural response to light should be sufficiently fast. Okay, so people use semiconducting materials like quantum wells, but it so happens that we don't need to do too much of all this. We can also use the Kerr effect in order to select the most intense pulses which are circulating in the cavity. So if I may go to my next view graph, so this is one pulse circulating in the cavity, but all of lasing actually begins with spontaneous emission and then goes into stimulated emission. So in a real laser, it's not one pulse. There are several such pulses which are making round trips and going around. A saturable absorber essentially absorbs light at low intensities and allows light to pass through at high intensities. So a saturable absorber, what it does naturally in the time domain is to absorb and kill all the weak pulses and let only the most intense ones survive. So in a sense, it is Darwinian. Okay, so that's what makes the laser pulses to be so what it is. We can write down equations, rate equations and dynamical equations in both time and frequency domain, and then show that the natural pulse that comes out of it is secant hyperbolic, okay, which is essentially a sort of soliton which is getting formed in this system. Right? This is a very interesting area of study. Colleagues in electrical engineering work with this and make such mode locked lasers, and one could also talk to them. I will skip these couple of slides in the interest of time. I'm just zooming into the same thing and showing you that essentially mode locking is producing an interference in time where at t is equal to 0, all the crests have lined up, and if this pulse were to propagate, the crests essentially did not line up at t is equal to 0, they started lining up at another instant of another location in space forward and in time, and the pulse moved. So all of propagation can be thought of in terms of these spectral phases, and in attosecond science and femtosecond science, these spectral phases are what we measure and make a huge difference. So this no Nobel Prize in some sense, at least today, comes alone and is a great standalone effort. It's literally on the shoulders of other giants. So it's just remarkable that in ultra-fast science itself, 2 Nobel Prizes have been given in a span of 5 years, which also probably makes the next one farther away in time. But these two people, advisor and student, Moreau and Strickland, essentially taught us how to make sufficiently energetic femtosecond pulses. Had this technology not been there, we would not have had attosecond pulses, as I'm going to try and convince you. But let's go back to Madame Lullier and see the harmonics that she generated. This is plotted on wavelength scale, which is a bit inconvenient, but each of these is a harmonic. These harmonics are odd: 9, 11, 13, 15, 17, 19, and 21. They have this shape because of the transmission properties of the optics, but if one carefully measures the intensity of each of these harmonics, and takes care of all these physical factors and plots them for a given set of laser conditions, you see this knee-shaped thing. There's a plateau and there is a cutoff. Okay, so what's behind these harmonics? This was a really surprising behavior, which is what led to this so-called attosecond revolution. Somebody turned on the laser, put rare gas in the and looked at the fluorescence, and then you see that these harmonics came about this way. This could have been anything: super radiance, some form of coherent emission, some which thing. So when I heard this from Anne Lullier, she said that she had a visit from none other than Ted Hansch, and Hansch told her, how do you even know this is coherent? In fact, that triggered her, and she thought, oh, maybe it could be coherent. So she went to the lab and put a pair of slits in front of it and indeed saw a Young's pattern. So it tells you that the emission is coherent. Fluorescence is not coherent radiation, or its coherence is very low, right? So this was surprisingly coherent. So that basically led people to think more about it. If that's the case, we might think, oh, conventional nonlinear optics can explain this away. You take omega, you know pretty well that it can convert, omega can be converted to green omega. Where does it happen? In every green laser pointer that you buy from Amazon, which one should be really careful about, actually has light coming out at about 1000 plus, 1035, 1064 nanometers. What we see is half that wavelength, which is 532 or twice the frequency, which is in green. That comes about because there are media where this second order susceptibility is high enough and we can produce the second harmonic, right? But then if this were to be the case, that's the clincher. Yes. So she used 1 picosecond or few picosecond pulses. I think she had about 10 to the 12, 13 watts per square centimeter. Picosecond. The first one was like, the gas was in a cell, it was not supersonic. So very, very sort of easy experiment, if you may. So, but these are harmonics that Lullier saw. They have a plateau and a cutoff, right? This cannot be the consequence of conventional so-called perturbative nonlinear optics. This region where there is a fall in the relative intensity along with harmonic order above the plateau is conventional nonlinear optics. So if you open the nonlinear optics textbooks, this is there in the first or second chapter. So therefore, once again, as Professor Einstein says, think what's happening. But this thought was kind of long thought, and although experimental work proceeded, for quite a while, we did not know as to why this was happening. And then came this insight to a few people, none of whom got the Nobel Prize, by the way. But here's the point. So if we take a typical rare gas atom and go in with a photon of about 1 eV, then photoelectric effect will not release electrons. It will barely even excite the atom. All rare gases are transparent to visible and infrared radiation, right? This is a very well-known thing. So then how does, if at all, how do we push this limit and get something else out of it? As early as in 1928, Oppenheimer already had thought about this problem. What if I subject an atom to a very strong field going beyond the known boundaries of Stark effect? Then he realized that the electron in this atom, the optical electron, valence electron, will have an opportunity to tunnel out, and in a static field he calculated the tunneling rate. So this physics was already available. The basic idea is the native potential of the atom is the minus 1 over r Coulomb, and then we come in with any field, static, time dependent, whatever. E dot r is the perturbative term. It is perturbative if the magnitude of the z by 1 over z minus z by r is much, much stronger than this, right? But then what if it was the other way around? There was another remarkable Russian physicist called Volkov. He took the other problem around. He threw away the Coulomb potential and said, what about a free electron in an electromagnetic wave? What are its states? They would be scattering states. So Volkov had eigenfunctions from the scattering states calculated. So somehow, in a way, ground had been prepared for all this to be done. But then that's how science works. We have an experimental result or whatever, and we try to work backwards to fit it. So this process of removing an electron from the atom with photon energies which are lower than the resonant energy using field-driven effects is called tunneling. Look at this little tunnel over here. It's a good undergrad problem to take a triangular tunnel or a sawtooth tunnel and figure out the tunneling rate in terms of the height and width of this potential. I think this is even presented in Griffiths as an exercise problem. So sometimes when you do that, you can come up with some remarkable physics as people did. But then Corkum came up with this very famous 3-step model, which is essentially rationalizing all this random, maybe Ptolemaic models of the electron's motion into what I would call a Newtonian physics-like revolution, in which he said, look, harmonics are getting generated due to the following fact. You have an atom, so this has a 1 over r potential, so which is like my hands, and think the electron is my head. Then when the laser field comes, E dot r, so the potential bends, yeah? So basically on one side it bends, and then the electron starts to see an opportunity to tunnel out. right? So then tunneling occurs, okay? So imagine my head rolling. Maybe there are people who want to see that, whatever that is. But then in the next half cycle, field flips direction. So it bends the other way. So the electron that was leaving its home, the teenager is pushed back because his credit card ran out of money, right? So then it comes back to the parent and then recombines. And in this case, only photons are emitted. Not only, there can also be electron scattering. But Corkum said this should be happening and this should be the basis for radiation emission because there is an electron recombining with two energies. One, it escaped the ionization potential of the static atom. So when it comes back and recombines, it should give us, it should emit photons with energy of the ionization energy, but it also had kinetic energy in the field. It gained some kinetic energy from the laser. So the electromagnetic driving field energy is also coupled and the electron falls back. And so we can expect that harmonics, if they come out through this mechanism, would have the IP plus something to do with the kinetic energy, which remarkably turns out to be true. So this particular paper.
But you can experimentally set up so that only the valence electrons are subject to this?
Yes, preferentially because the tunnel rate depends upon the ionization potential. So we can say predominantly, we at every, suppose I have the valence electron, I take an alkali atom, lithium, it has, so the first electron is easy to remove, so that will come out. We then, if we want to remove the next electron, I need to have a threshold intensity before which the next guy comes out, and that is quite substantial. So we can ensure that we are playing with the valence electrons. Actually, Russian theorists had also calculated some of this well before. So I think people had could take advantage. Yes.
You will not have too much energy so that it just gets ripped off.
Okay, that will take a tremendous amount of field. I don't think most lasers can do it for a substantially large atom even today. Yes, Raj.
The tunneling picture seems very nice, but where is the fact that what we get out is in the attosecond?
Yes, we are coming there. So we're going to pay tribute to whom I would call the Isaac Newton of attosecond science, who didn't get the prize, but he has been honored tremendously. If you talk to somebody in the field, they would share a certain sadness that Corkum was not recognized, but I don't want to go there. He's a remarkable person. But then he had a single author phys rev letter which explained this, and today it's touching 9,000 citations. Everybody likes to cite this, right? So that's the person, the physics, and the journal. He basically did a PhD in theoretical StatMech, and then went for an interview somehow to NRC Canada, and he wanted to do experiments, and this I heard from Corkum's own mouth, that they asked him, what makes you qualified to do experiments? He said, if you come to my garage, I can take apart my car and put it back. And they were apparently convinced. But then that's the elegance with which he did his maths too. He said, okay, let's do the Newtonian physics. Basically write down the equation of motion for an electron that is somehow just come out of the atom. He said, let's not worry how it comes out of the atom, because if you think about energetics, all that happens is it has gained an energy equal to the ionization energy, and it is just nascent in the continuum, driven by the oscillating laser field. Solve this, go from acceleration to velocity to position, and note that for an electron driven in an electromagnetic field, again a question of scales. What is the energy scale? It's the average kinetic energy, which is essentially the square of the charge times the intensity, which is E0 square, divided of course by the mass of the electron, but divided by the frequency of square of the radiation, or proportional to the square of the wavelength. So I lambda square is proportional to this average kinetic energy. So this was his observation, and then he simply said, at what time during the oscillation of this incident electromagnetic wave should the electron be born, right, as it happens in mythology, special times when it is born, so that it gets the maximum advantage of the kinetic energy from the field. Because remember, the harmonic spectrum has a cutoff. So if I can explain my cutoff, my model should at least be doing somewhat right. And he did this based on Newtonian physics. It is well known that from empirical data even by then, that the cutoff energy scaled with ionization energy and this UP as IP plus 3.17 times UP. You simply did an undergrad problem and pop comes this result out, that if the electron came out with a phase of 17 degrees or 197 degrees, taking any one optical cycle in this in the electromagnetic wave, it would essentially have the maximum kinetic energy, which is 3.17 times the average kinetic energy, and if it recombined, it gave you the harmonics back. And so he called it the plasma perspective on strong field multiphoton ionization, right? So remarkably, this model, which is popularly now called the three-step model. First step, tunnel out. Second step, make an excursion in the continuum, that's almost field-free stuff, but driven by the laser. Turn around, come back and recombine with the atom. That essentially was the only model to basically make in order to explain the broad shapes of this harmonic spectrum. One, perturbative region, go away from it. This explained why there is a plateau, and this also explained why there is a cutoff. So the three-step model is a simple man's model, and it's very successful, right? Around the same time, very likely without knowing about each other's work, Ken Schaefer and Ken Kullander, who are now in Louisiana State, at least Schaefer is in Louisiana State. So they actually did a very nice quantum mechanical calculation, and I think published it in a conference right about the same time. So Newton's laws and elementary Schrödinger-based quantum mechanics work very well to explain this. This was a very similar approach, right? But then I think
acceleration.
Pardon?
You said acceleration.
Yeah, yes, Srinath.
So this is because of the electric field driving the electron.
Because of the laser field driving, E times E.
Yeah. And then, it just loses energy.
It gains energy from the field.
From the field, I understand.
Yes.
It loses energy and falls back in.
It should be losing some radiative energy, but that's a small factor. But it's essentially gaining kinetic energy from the field, then going around like this. It goes around up, away from the mother atom, and then comes back. And collides. The rest of it is actually a collision of the returning electron accelerated coming back to its parent
That's
ion.
a classical picture.
The classical, yes. So the wave picture, I'm coming to that. But we can literally just put a wave packet, a Gaussian wave packet. I'll just come to that in a moment, right? So, but here comes the moot point as to why these pulses are attosecond. Yes, please.
That quantity, what is maximum at omega naught t naught?
The kinetic energy gained by the electron from the driving field.
That UP is maximum.
UP is maximum. Literally, it's like buying a share in the market. You buy it at the right time and it could.
So what frequencies of that incoming laser, are there bounds on the lower frequencies of the incoming?
No, it just needs to be something that can remove the electron out. So this has been done with a whole lot of stuff, even with microwave radiation, with Rydberg atoms which have somehow been with electrons raised to very high principal quantum number orbitals have been studied very much. Tom Gallagher has done a lot of work in that.
What sets the scale of the cutoff?
It is basically the max energy the electron or the wave packet can gain from the driving laser field. That turns out,
Laser field that sets the cutoff.
that sets the cutoff, yes. Its intensity and its wavelength actually. So it's basically doing a slingshot. So now this actually tells us that attosecond pulses are nothing but a consequence of sub-half cycle phenomena happening at every half cycle of a driving laser. So this, if it is 800 nanometer lasers, one period is 3.3 femtoseconds. So each half cycle is 1.65 femtoseconds. But one can imagine that a field-driven phenomenon mostly occurs close to the field maximum. Right? Tunneling, the primary step will occur close to this maximum of the field. Right? So therefore, all these events are localized very much to this. So every half cycle, there is a burst of radiation, which is a traveling wave, a pulse, which is what we see as attosecond pulses, much like this. So if I take a wave, which is like a continuous wave, this is unrealistic, and generate attosecond pulses with this, I will have one attosecond pulse every half cycle, right? So there are two pulses in every time period of this, of the primary driver. Therefore, the harmonics that come out of this process will essentially have twice the frequency of the driver, and so I see omega plus 2 omega is equal to 3 omega, plus 2 omega is equal to 5 omega, plus 2 omega is 7 omega, and so on and so forth. So normally high harmonics generated from this process are odd harmonics, 1, 3, 5, 7 and so on. There are also symmetry reasons, but this temporal region is just as fine. Okay, so now we can explain in some sense, but rigorous theory has done it very well, to explain the shape of these attosecond, of these high harmonics. So these harmonics are, that's the thing, extremely coherent, extremely coherent. We can make, people are making frequency combs with this, and these generate attosecond pulse trains. How do you measure it in the lab? This is just a cartoon view of the same. If this is the process of tunneling and everything, the three-step model is playing around with the red driving wave, then you put a grating and then a suitable imaging detector, and there you have the harmonics coming out, right? Even the shape of this harmonic is gotten very well in it. I will just make one remark that it is a fully quantum process, as you might like, right? If you simply take this one particular harmonic, you can pretty well explain as to why the harmonic is there in terms of the frequency where the spectral line should come, but why the shape? Why any distribution along the vertical? That's because there are many quantum paths coming to an interference, and there is the short trajectory and the long trajectory, which are basically sampling the mother ion's potential, and there are people who do spectroscopy of just one of few harmonics in the other direction and learn a lot about the quantum dynamics going on. We will not have time to go into that, but then how do you put all this together in a proper quantum mechanical formalism? In this paper, not in this paper, I'm missing citing that, in a paper which is famously first co-authored by Leuenstein, it's the Leuenstein model. Today Leuenstein is doing a lot of quantum information too. So he wrote down the dipole moment in terms of this integral, which has three parts, and the first step is ionization in this Leuenstein integral, which is somewhat phenomenological. First step, ionization, is taken care by this term. So in terms of where this happens, this is pretty close to the node of the 1 over r field, which should be right in the middle of this Gaussian looking wave packet, which is the wave packet corresponding to the ground state of the system. Then there is the propagation phase. So it is accelerating there. It's a quasi-classical action written down in terms of the canonical momentum of the charged particle in the electromagnetic field. And then recombination is this third term. So that insight which Corkum got, Corkum, Schaefer, Kullander got, was put in formal terms by Leuenstein, and this is how people do calculations these days. So this is quite a formidable calculation for even small atoms and molecules. A technical point, I will just gloss over it by saying that just like all of the harmonics, one should do not just energy matching, but it's the experimenter's job to do momentum matching. So do the phase matching well if you want bright enough harmonics. Unfortunately, the harmonics which are generated in attosecond pulses, the conversion efficiency is rather poor. For every million or so driving photons, you get only 1 or 1 to 10 harmonic photons. It's a very, very inefficient process as it stands today, which is why the driving field needs to have substantial energy. Okay, I'm really running out of time. So I will also try and accelerate to give a flavor of what it is. But here is the moot question. If you make the shortest events known to man, then how do you measure it? Who's going to give? This is very much akin to Professor Sriram's question. Where does the other shortness come from? Right? So we know it's common sense that the minute is kept by the seconds hand, and the second is actually kept by something millisecond down there. So if we made an attosecond stopwatch, there should have been a zeptosecond ticker, and there is none. So how do we measure them, right? So this is where the other two laureates come by, especially Pierre Agostini. So he devised a technique which is popularly called something, but I will come to that. But the basis for all this was laid 100 years ago by Michelson. Okay, why do I say that? Is it because he took a beam splitter and two mirrors and did stuff? What was he trying to measure? He was trying to measure the fringe shift due to these two configurations of ether and whatever else. We teach this in several courses, right? So let's do a simple back of the envelope calculation and determine what this t parallel divide minus t perpendicular is, right? So the Earth's velocity 10 to the 4, in vacuum speed of light 10 to the 8, v by c 10 to the minus 4, and it gets squared in this case. Length of the interferometer about a meter, in his case 1.2. Right? What is the time difference? He was trying to measure a time difference of 80 attoseconds. At some point, this was the Guinness Book record for the shortest attosecond pulse that was man-made, right? So, and he indeed saw a null result, which was at visible light frequency had to be 0.03 period. He didn't get a fringe shift. It's a matter of history that Michelson never believed that this experiment was a success. He believed that something was wrong with it and took that to his grave, even though Einstein was his pretty good friend. But in the process, he laid the foundation for attosecond metrology and probably even detecting gravitational waves using interferometers, because he showed with 1880s technology, when horses were among the primary mobility instruments, that you can do 80 attoseconds in terms of measurement, right? So people took this idea in terms of making such an interferometer. This interferometer, every interferometer needs a beam splitter. So we do a cross correlation between the pumping pulse, which is in red over here, and the blue pulse is the turquoise pulse is the attosecond pulse, and these two are essentially extremely coherent, and so without too much mutual jitter, they are overlaid one on top of the other, and then these are focused onto a gas jet. Okay, so if two electromagnetic waves crisscross each other in any volume of space, then they pretty much do nothing if it was just linear interaction. Two light sources are here. We don't observe interference for many other reasons, but even if we had just two beams crisscrossing, we see an interference pattern only in the volume where they mutually share. Otherwise, we don't see. Now, if you want a lasting signal, you got to have some nonlinear interaction. In this case, that is the again, rare gas atoms which are put there, and the electron spectrum of the rare gas atoms turns out to be the signal. And then this is an interferometric measurement which is called Rabbit, reconstruction of attosecond beating by interference of two photon transitions. Very interesting, but I will break it down in very simple terms. This is a standard interferometry technique, but remember, the question is not to measure an interference. The question is to be able to retrieve the participants in the interference. I need to know whether I had an attosecond pulse at all or not. So P. Agostini, when he first did it, he had some foggy idea that there may be pulses, but it could have been anything else too, right? So one had to really believe in that. So if I take various harmonics, harmonic Q, Q plus 2, Q plus 4 and so on, and basically ionize an atom from its ground state, in the continuum the electrons that come about, right, would essentially have kinetic energies which are like these spectral lines, but on this is superimposed basically the mother driving field which made these harmonics, which is at omega, right? So because these guys are extremely coherent, a sideband is formed using in this case Q plus a 1 over here. There's a frequency mixing. So if this was 3 omega plus omega, this is a 4 omega line, there is a 5 omega here, and the same nonlinear optics tells us there can be a difference frequency mixing also. So 5 minus 1 omega, 4 omega. So the sideband that is formed here is essentially formed by a coherent superposition of two of these main lines. So that is the satellite. So this is what he realized, that if it was harmonics, then it should be this. They had this, and then they gently varied the mutual separation between the harmonic, the high harmonic and the high harmonic pulse train, and basically the mother driving field itself. So if the harmonic was perfectly matched with the mother pulse, it's like this. If it was shifted by a little bit, then basically it came out of, it moved quarter of a period, and they did very fine scans over one quarter cycle of the driving field. And this so this is a student I co-advised at MPIK. So he made this beautiful rabbit spectrum. All the information that we need is contained in the sidebands. So I'm just showing you one sideband here. I'm not going to belabor the point that using phase retrieval algorithms, which today we know very well and comes a lot more out of imaging science, we can actually get complete information about both the driving pulse and the attosecond pulse. In this case, people were more interested in getting information about the attosecond pulse train. Okay, so this is just a neater diagram. I will push forward to make this point. I will, and since I'm running out of time, I will really skip out the details, right? So the next step, which is basically the main contribution of Krauss, comes about by the following observation. Now, if I had a pulse like this, I would the driving pulse, the red is the infrared optical driving field. Let's say that the two most intense half cycle produced 2 attosecond pulses. And I did the rabbit measurement, right? Rabbit is essentially a photoelectron spectrum. So I'm plotting the photoelectron spectrum on this vertical axis. You can see a negative energy there. The negative energy is because I'm essentially measuring an offset energy, which is plotted as a function of delay. So bear with me, it's correct, it's not a typo. But the point is, if I had 2 attosecond pulses, which are spaced by a half cycle in any form interfering with the mother laser, then I get 2 peaks in the spectrum. We will quickly and clearly understand why this happens in a short while. But contrast this scenario with the following. Suppose I had a single attosecond pulse, okay, which is, let's say, the driving laser had a period of 3.3 femtoseconds. The attosecond pulse had a period of just 0.3 femtoseconds, right? So then what happens? Then the photoelectron spectrum on this scale looks like this. It's very simple. All spectrometers convert spectral information to spatial information. We put a camera at the end and then we measure. Why? Because we don't have a way to measure spectra. All time measurements which are done on this scale essentially map time to some other variable. More often than not, here it is energy. In some cases, it's even space. But here we map time information linearly onto energy on an energy scale and measure energies because we know how to do this very well, right? So basically, now we can do something which people had been doing very well for nanosecond lasers and so on. Suppose the shortest pulse I had was picosecond or a nanosecond pulse. How did people unambiguously measure its time structure? They did something very smart. So they basically let the initial pulse go through a photocathode, and photoionization is an instantaneous process, as we know. We can question that now with attosecond pulses. You create an electron bunch which essentially has the same time structure as the pulse, and then pass it through a pair of electrodes, and then crank up the voltage pretty high to up to a kilo electron volt in a very short time. What this essentially does is it basically flips the time structure of the electron pulse, which was like this, into a spatial structure. That's what the fast rising gradient does. And then you just image the electron bunch on the screen. You got the time structure. This process is called streaking. So Cross and Corkum got this brilliant idea that I can use the mother field, the strong infrared field, which was strong enough to create harmonics, because harmonic generation is a very inefficient process. Less than 1% is actually consumed. So recycle that pulse and use the mother pulse as the streaking field, okay, and basically let the attosecond pulse create the photoelectrons that one needs to do needs in order to do make the streak camera work. But then the physics for this is something we very well know from our course on Lagrangian mechanics, because the momentum of such an electron, okay, has essentially two components. It comes out with a certain momentum from the atom, its kinetic energy, soon after its ionization. This is essentially the photon energy h nu minus the ionization energy of the atom, h nu minus IP. This gives it a momentum, that's the mechanical momentum. But then the moment it starts working around in the field, it has the momentum due to the vector potential of the field, right, which is A of t. So Landau-Lifshitz P plus QA is the canonical momentum. This is the true momentum of the electron, and this is something which they were smart enough to exploit and realize that depending on when the electron that is released meets the laser field, it will have different momentum shifts. The delta P essentially is because we are measuring the shift as against the mechanical momentum of the electron, which is nothing but h nu minus the ionization energy, right? So in a more sort of graphical way, essentially this is what happens. If I make an interferometer and cross correlate the mother pulse, the driving pulse with the attosecond pulse, as this attosecond pulse scans through the driving pulse, it produces shifts in the photoelectron spectrum, which essentially map the field for me. That's attosecond streaking or an attosecond streak camera, okay? So if you did this in early 2000s, you got a science paper and you were literally on the cover. So Leftherios Kouliamakis was a PhD student with Krauss who made this, what I would think is the most iconic iconic of images, because if we took seeing is believing too literally, this is the first time humankind saw a petahertz visible oscillating electric field or a signal corresponding to that. Okay, so it was a cross correlation measurement which did this. It was, then we can fit things out and do all the math and then calculate very nicely the electric field of this driving laser pulse. So now what did we just do? We made a petahertz oscilloscope, right? In an oscilloscope also is a cathode ray oscilloscope was also streaking our signal, just that we didn't know it because we pressed auto trigger more often than not, right? So, but the point being that we have an oscilloscope. So this is technology from physics labs. Currently we are in gigahertz technology, but this is petahertz technology. Can we really exploit it? How are we going to exploit it? I'm just going to make two statements about it. Maybe in future a petahertz electronic chip would look something like this. So the point that we are broadly making is that what we are doing is controlling doing electronics which is field driven on petahertz time scales, right? So if you look at these two pulses which I have plotted here with reference to the maximum of the envelope, in one case the carrier maximum is right on top of the envelope. Okay, so if I can write this down in terms of a phase, this is 0 phase. In this case there is an offset. The carrier and the envelope maximum have shifted out by a delta phi. So this phase is called the carrier envelope phase. This is an example of something like an absolute phase in optics. You can never really measure absolute phases. That's a statement that a lot of people like to make, but that's true only for linear optics. If I want to characterize this pulse, it turned out, again this was work done in Krauss's group along with Gerard Poulos. So they realized that these fields can be quantified by what we call the up-down asymmetry. Suppose I have a process that has a threshold, okay, plus or minus some E naught. Only fields above this will create photoelectrons from tunneling, which is quite true, right? So then in the case of this first field, on the upside I have 3 peaks, only 2 peaks on the bottom side satisfy this condition. So if I get any signal out of this and I put 2 detectors, one at the bottom and one at the top, and did a balanced measurement or actually an imbalanced measurement, people do this, balanced photodiodes are there in a lot of optics labs, then essentially we will get a difference signal. So this difference is essentially a characteristic of the shape of this field, provided I know that broadly this laser is capable of delivering such fields only. Whereas in this case, the difference is the second case to the right, it is going to be nearly 0, right? So the carrier envelope phase is a single number which, if I produce good signals and pulses, will tell me how the pulse looks like. This is not new. All light pulses carrying information on optical fibers are not chaotic, random or whatever. They also are well prepared using good lasers. So we are not asking for anything extraordinary, but we are giving a metric for qualifying these pulses, right? If this is a very good few cycle pulse, then like what I've plotted in the bottom, we can get a very good contrast signal. And this is an experiment any of you can build from scratch if we give you enough money to buy the laser also, which is pretty expensive. But then folks took advantage of this. Basically, they built a petahertz switch using these light waves. Any measurement of petahertz electronics should be something plotted as a function of carrier envelope phase. Okay, so that is what they did. So here in the bottom plot, you see the conduction band population of silica, which is a pretty good dielectric. Okay, so a pulse is incident between just a piece of glass with 2 electrode pads made on top of it, and here you have a very simple lock-in voltage or current measurement. They basically measured this as a function of carrier envelope phase and did, of course, a very good piece of condensed matter physics or materials modeling, and simply got the full detail about what is happening in the silica and showed that in light field driven electronics, we have FETs. If we had LFETs, light field effect transistors, then these switches would actually be better than conventional switches, because conventional switches are based on semiconductors and there is some leakage current. In dielectrics, this is the lowest. So if you do this in reality, it's going to be fantastic. Now, using graphene, Peter Hommelhoff's group showed that I can indeed drive a transistor-like behavior with graphene on SiC with 2 pads over here and get signals out as a function of the carrier envelope phase. Peter Dombey's group showed this with all the nice electronic grade materials that we like to see: silica, hafnia, high K dielectric, and GaN, high power. So what more do you want for doing futuristic electronics? Yet it's going to be quite some time by which we are going to by which time we are going to have these devices in our tables or pockets. Now, in the last couple of minutes, we want to pay a tribute to Einstein, who makes us think a lot, right? So, Hensch and Schwallow said always count frequencies or measure frequencies. They are the most precise. Krauss and Corkum, by inventing streaking, said always measure times or time delays, right? So, what can we do with these time delays? Okay, that's the question. Now, Wigner in the 20s took up this little problem that if I had a wave packet scattering out from a potential, then he said that the wave packet scatters from a potential. You have the blue line and the gray line. The gray line interacted with the potential, whereas the blue did not. If I may just run it through, between the two wave packets, one that doesn't see the potential and one that sees the potential, you essentially have a delay between these two wave packets. So he computed this. This is called the Wigner-Eisenbud-Smith time delay. So if you have an atomic potential and you do photoionization or any scattering from this, you have a wave packet which is as it would have been without the potential, and you have a wave packet which has interacted with the potential. Except, like in the case of Michelson, it's difficult to have both these coming out of some electronic beam splitter, right? So clever guys, they did this. They compared essentially, did two streaking chronograms, one by ionizing an electron out of the 2s state of neon using 100 eV attosecond pulses, another from the 2p. They are about 10 eV apart, and it's very difficult to see in this, but the two maxima actually are different by just 20 attoseconds. On this time scales of thousands of attoseconds, it's of course impossible to see, but they did a proper retrieval algorithm and got this delay out. So if atoms work, can condensed phase be two behind? We actually want to build condensed phase devices. This is photoelectric effect from the 001 phase of magnesium atoms. They did, this is 2p, and the plasmon satellite of this metal in this direction, and they measured the photoionization time delay between these two. It turns out to be a very impressive 60 attoseconds, but then this was the ultimate experiment in terms of a lot of questions in the community being raised about exactly what this delay is about. Are you measuring it right? It's 20 femtoseconds over 20 attoseconds over 4 or 5 femtoseconds, and so on and so forth, in a very clever experiment in which things were self-referenced. Kienberger and others essentially measured streaking traces with helium, with iodine, iodomethane or iodoethane, and the surface of tungsten, all using the same spectrometer under nearly identical conditions, and got 3 chronograms, and from this unambiguously showed that there is a delay in the photoionization of tungsten with respect to the others, referencing it to helium and whatever else, to show that photoelectric effect is not really instantaneous. It takes a few 10 attoseconds for this to happen. So maybe if Professor Einstein were here, he would have maybe applauded this photoelectric experiment, right? So next, I'm again not going to go into the details. You can take this to the ZILT, do chronoscopy instead of spectroscopy, and then get some visual ideas. This is a double slit experiment, but done in the spectral domain. Take krypton atoms, and krypton is basically ionized by removing an electron out of the 4p orbital. The 4p orbital is spin orbit split. You have 4p with -1 with j half, and j equals 3 by 2. So while this was created by a few cycle optical pulse by doing some kind of tunnel ionization, Guliel Marquez and co-workers ran through and did a streaking with an attosecond pulse, which essentially took this ground state ion and made it to a 3d-1 excited state ion. Looks like pedestrian atomic physics, but then both these pathways going through two spin orbit states reach the same screen, and are degenerate. Therefore, we have a double slit experiment going on over here. First wave comes about, that's the two paths. I mean, there is no which way information, and then you have this coming about, but in this case, the fringes appear in the time domain, right? Because the slits are in the energy domain. In the conjugate domain, you get the fringes. So then you do some nice theory and literally show that these orbitals are beating, just the way I had shown very early on. This was quite a remarkable effect, and I will literally close with this. We can do dynamics. Can we control, right? Because control is everything. All of quantum technology today is about control. The two electrons in helium atom were entangled since they were born in the universe. But you can't make a quantum computer out of them, nor do high quality sensing. That's because we can't control them. They are what they are, right? So can we control electrons? Let's take the textbook three-body system, which is helium itself. And so if I photoexcite helium so that it goes from the 1s2 to 1s2 state to the 2s2p, doubly excited state, what do I see? We must have been taught about this in atomic physics. If not, maybe it's something for those into it. We see a bound state embedded in a continuum. So we see Fano resonances, which are not just here, everywhere, yet they were discovered actually in helium by Ugo Fano. And there's this very nice paper by Domke and others which details this out. Everything about the shape of this resonance is essentially pinned to the so-called Q parameter. Okay. So my friend Christian Ott, as part of his PhD thesis, did this really beautiful experiment where he took an XUV pulse. Remember that we are Fourier limited, so a very short attosecond pulse with a central photon energy of 100 eV has a bandwidth of about 10 eV. Okay, so it is pretty broadband radiation, but it is very coherent. So it excites several of these states, excite with a short yet weak XUV pulse. And how do we introduce control in this? Basically couple it with a partner field which is very coherent. Who's the partner field? The driving laser. So use that. So Christian did this really ostensibly simple experiment where he varied the mutual sort of delay between the XUV, that's the attosecond pulse, and the visible, and simply measured absorption spectra. This is transient absorption spectroscopy, as we like to call it in the XUV domain. And when the visible laser came first, helium is untouched. It has an IP of 25 eV almost. So you measure the Fano line here when the XUV comes later after the visible pulse. But then, if you really see regions where these two pulses overlap, this Fano line has changed its shape. Okay, so is it just, in a way it is getting stark shifted, but this is a very dynamic and stark shifting from a very strong field as well. So all this is happening because, just like in the case of rabbit, there is a coherent interaction with an intermediate state, and I will not go too much into it as they crank up the intensities. It's just a sort of quantum, maybe say, magic carpet, which is where the spectral lines are changing. But what's leading to these beautiful patterns is the following, and I will stop with this more or less. Typically, line shapes we know are Lorentzian for individual line shapes or Fano. What does control mean on these scales? Essentially, you change the DNA of the atom, so to say, or control it, right? As in science fiction movies. So they could at will, by turning just one knob, the intensity of the driving visible field, change the line shape from Lorentz to Fano and Fano to Lorentz almost at will. They also did this in terms of temporal dynamic study later on. So that's the control at attosecond time scales of angstrom scale quantum systems. So with that, with apologies for overshooting my time considerably, I hope I'm forgiven, at least partially. I'll thank you for your attention and take any further questions.